All right, so those are the couple of terms you'll see is interparticle attraction and then a sea of delocalized electrons. That's just another way of saying exactly what we said, attraction, and that's it. And when I say anytime I put VE here, what does it mean? Valence electrons. So if you want to write any of that down, you're good. Most of you look good. Okay, alloys. So we talked about what these properties, that metals have these properties, but why? The only part you really need to know is that if I have a wire and you've got all these cation or metals in here, their electrons are delocalized and they're free to move. And so that's why the conductivity exists, because the electrons are not stuck in a location, they're free to move. That also explains why the ability to flatten it or put it into a wire exists too, because whenever you try to pull a metal apart, don't you think it'll rip in the middle? Why not? Okay, can I bend it and break it? Right, if I was like the Hulk and I could bend it and break it. But a metal, the reason it doesn't break immediately whenever you try to stretch it is that every time you pull a wire this way and this way, electrons fill the gap. And what are they attracted to? The positives. So when electrons fill the gap, what comes in with the electrons? The positives. The positives come in here and fill the gap so that it doesn't break, so that you can keep pulling and stretching it out to that long wire, whatever you're trying to make. Trying to make a flat sheet or whatnot. So that's why metals are so durable, because their electrons move and they fill the holes as you are causing stress to it. And then that's in contrast to your ionic stuff, because ionic stuff's like, you stress it a little bit, this structure, lattice, you throw it on the ground, it shatters, it's gonna break. There's no electrons filling the gap, they're stuck in a single location. They're not as durable. And then this is the alloy part. So these are just two examples of common alloys. Yeah.
Did you say ionic bonds are not stacked up because their electrons are stuck in one location?
Yes. Yeah. They don't have those properties because they're stuck. Two alloys. So Dale Earnhardt, who remembers when he met his demise? Okay. I don't watch NASCAR. Okay. In Kannapolis, they've got this nice big bronze statue of him and his majestic self. And it doesn't tarnish. Like the Statue of Liberty. What's on the outside of the Statue of Liberty? It's green. What's that green stuff called? Anybody know? It's not organic. It's actually a metal. It's called patina. Patina is oxidized. Oh, thank you. Whoever said it. It's oxidized copper. So when I think it was France, I'm gonna tell you I don't know history, but France gave us this, and it was a really pretty kind of bronzy colored, somewhat bronzy colored statue. And so over time, it's been somewhat reactive. It's been exposed to all the elements, so it's oxidized. It's turned green. Why is it green? Because copper. You know the copper flame? It's like a blue-green color. That's the reason why it's green, because copper exhibits a green color sometimes, which is why you'll see like pennies that have that green color on it, because it's got copper in it. So they didn't do a fantastic job of making that alloy, and that's why it's reacted over time. Dale Earnhardt Jr., we made his statue fantastic, and he has not changed at all. But it's a mixture of copper and tin, which makes it this is actually the more durable or unreactive metal, and the copper color just makes it pretty. That's why we put those two things together to make a bronze color. Do you guys know what are in pennies? What two metals? Copper and, I heard somebody. Zinc, thank you. It's got copper and zinc in it. That zinc provides some durability to it as well. The reason I'm having you bring in 1983 pre and post pennies are because over that time we started saying that the penny was worth more than a penny. So people, jingling change in their pocket, had more money in their pocket in the pure value of the metals than the actual cent, 1 cent was worth. So we had to change the ratio so we weren't wasting money.
Sorry about that. Have you heard them call the usual word of activity?
Yeah, that's why that whole alphabet's on. Bye. Okay, so anyway, we're gonna do that live tomorrow, and you'll see how we work with that. The other one is cast iron. So like grandma has this big cast iron skillet. Why does it work so well and retain the heat so well? Carbon, the heat remains in the metal or the pot more readily. That's where the carbon comes in. It retains its heat really, really, really well. Iron, on the other hand, why would we need that for cooking? Conductive. Thank you, thank you. Okay, because it's conductive. So we need that so that we can have that, that transfer of heat from the stovetop to the food. Otherwise, we can't get it. So that's why cast iron is really durable. The heat kind of stays with you the whole day if you keep your cast iron skillet on the stove, and the iron is there because we need a metal conductor. Okie dokie. All right. So this is all that we're gonna talk about alloys a bit more tomorrow. So everyone else will catch up with us and we can make it happen. All right. And then this is what I was talking about, the carrots. So how does this work? I'll talk about that in a second. Okay. So when you get to be my age, and you find somebody, and they say, "Will you marry me?" They're gonna give you something like this, okay? So, and they are gonna say, "Oh yeah, girl, it's 24 karat gold." I'm gonna say, "I don't want it. I want the 14 karat gold one." They're going, "I like this girl." So, because these are more expensive because they're pure, I want it for the durability, right? Because we talked about it's kind of bending and stuff. 14 karat gold or silver or whatever, it's actually not 100% anyway. It's got all these other things in it because we want to make a really good, long-lasting piece of jewelry, whatever it is. So, this one actually has about 10 carats of gold for 24 karat total, and so forth. This one's got 14, so this is a little bit less than 50% gold. This one's a little bit more than 50% gold, and so forth. Even though that's more valuable, this is more realistic and, reliable for you throughout your life. See how the ratios work? Okay.
You have like a 24 karat gold ring. How easily does it bend? Is it like really, really probable that your ring is just gonna get all distorted?
Usually if you carry heavy things, like my baritone, carrying that around every day, long, constantly wearing and carrying on it, yeah, it's going to bend. It's going to make that circle, and so it'll have a flat spot on the bottom. But a lot of times you can buy 24 karat necklaces because who's laying on their necklace, right?
Yeah.
So necklaces and earrings are mainly more 24 or 18 to 24. Bracelets, rings are commonly this way because you work with your hands a lot. Mm-hmm. So it's better for long-term durability if you have this stuff. So guys, explain that to your girlfriends when you get to that stage. It's cheaper, I know, but it's better for you. Okay, this is also on your sheet. Why bonds form? You need to know this one for sure. And we're just going to do a little bit of bonding so we don't get too far ahead of the class, and then we'll make our fortune tellers. Okay, we're going to call them fortune tellers. So this is on the top of your sheet. If you look, it says why do bonds form? Or you can write it, wherever. This is right here. Why do bonds form? And that have a crash course. Who's ever seen crash course chemistry? All right, or crash course U.S. history, or crash course. I don't know what else they do. Military history. They have a lot of really good videos, and I'll show you a brief, kind of maybe 5-minute clip of that. All right, so if I have, let's say, nitrogen. So we all know that nitrogen makes up what percent of our environment, our atmosphere? 70-something percent. 70, let's say 75, just keep it real. Okay, so we've got nitrogen, that's diatomic, right? What are the other ones that are diatomic?
Fluorine, oxygen.
All right, how do you know it? The big seven. Okay, so fluorine, chlorine, bromine, iodine. The AT one you don't see too often.
And then
Oxygen, thank you. Okay, so nitrogen actually looks like this when it bonds. What kind of bond is between it? And okay, that means they're only with organic. It's only with carbons. Sorry, but good try. Okay, so that is a triple bond. So why does this even happen? So we've got one nitrogen over here, another one over here, and they say, hey, let's bond. Why? There's got to be a purpose. It doesn't just happen. Chemistry is not willy-nilly. There is a purpose, okay? Why? Okay, to get octet is actually the real reason, But why is like octet? Why?
Because that means that there's no valence electrons in the whole outer shell.
Okay, which makes it more stable. We saw, right? Okay, so it makes it more stable. So this has high energy by itself, and this one does too. But when they come together, yeah, it's like a compromise. You're like, okay, I'll share 3 with you if you share 3 with me, and it's a compromise. So there's a reason for this, so that they can both have octet at the same time. Yeah, they have to share, no biggie. So that's where the octet comes in. And then the ways that we form our bonds, this is obviously, if they're sharing is covalent. If I were ionic, I would have to say, yeah, you can totally have this electron. I don't want it. Like sodium. Sodium's got that one valence electron. It doesn't want it. Who would it be likely to give it to? Huh? Chlorine. Chlorine's a really good one. So chlorine has how many valences? 7 valence electrons. So this Mother Teresa donates to the poor and gives it, because once sodium gets rid of it, who does it get to act like? Noble gas, and so does chlorine. Win-win situation. Okay, so ionics are going to donate specifically if they're like really far apart. So sodium's way over here, it's like ready to give up that electron so it can bounce back. And then chlorines. That's what we say see ionic compounds with metals, which are way over here, and non-metals. Nitrogen, on the other hand, nitrogen and nitrogen are both non-metals, so they're like, no, we both need electrons, we need to share, we can't donate. So you gotta make sure you think about if it's a metal or non-metal too. And then this is already, you've already written down some of this. This is the only thing I need to add to that ionic and covalent part of your chart. So you notice that between sodium chloride, where we put sodium chloride at like 800 degree for its more like, was it sodium chloride or sodium oxide? Chloride, okay. And then magnesium oxide had 2852. Ridiculous change, right? Why? When I say depends on lattice energy, charge, product. What's product mean in math? Answer of multiplication. So when I say charge product, what do you think I'm multiplying? Okay, so sodium chlorides, what are its charges? 1 and 1, right? Yeah, that's a 1 plus and that's 1 minus, but so 1 and 1 equals 1. So this 1 correlates to having an 800 degree melting point. If you have a stronger or a larger charged product, your melting point goes way up. So what's the charged product between magnesium and oxygen? Oxygen has a 2 because it's in the 6th group. Okay, so that's a 4. So if I had you compare something, if I said, who do you think has a higher boiling point? All you got to do is find their charges, find the product, whoever has the higher product wins. So like aluminum oxide formula. Aluminum oxide, charge 3 plus, oxide 2, charge product 6 versus calcium chloride. Chloride has what? Okay, Jose has a 1. Okay, so that's a 2. So who would have a higher bonding lattice energy? Aluminum oxide. Easy. Just got to know the rule. That's it. Question? Okay, moving on. Oh, I didn't say this one. We're going to talk about how we have shapes and like, do you think, okay, so if I have a single bond, a double bond, and a triple bond, and I'm a, black belt karateist, not sure if that's right, but the terms like this for me, I'm not going to hurt you. Okay, so if I want to karate chop this, how much energy? How many bananas?
A lot.
3.
Okay, 3 bananas, okay? Can I get a double bond? Make it work. Alright, double bond. Okay, 6 bananas. Okay, and if I have a triple one, like crazy amounts, right? So as I go up in the bond, like single, double, triple, it's going to take more energy. And then there's some other stuff that goes into play. You don't want to know that yet. So this one's going to be the least energy it takes to break, all the way down to the most energy it takes to break. Mr. Lowry's not in on that. Inside joke, bananas, but so, alrighty, ready? Okay, and then my crash course is, oh, one more more. I've already shown you this. I'm skipping this. Okay, crash course. We have a model called bonding, and I'm gonna show you the very beginning because it's kind of funny, and I like funny stuff. John, yeah, you've seen John Green on. Oh, okay. I was thinking stuff that blow your mind or something like that. Okay, why is it speeding through?
Oh, because if you have it.
Oh. Okay, there we go. All right, listen to a little bit, and this first part's funny, so I want you to see it, and then I'll show you the rest. What have I done, guys? I'm not this technologically challenged. What have I done? Stop it. Okay.
Models are cool. Ah, those models. I actually find that particular cultural institution pretty peculiar. I'm talking about the kind of model that lets you experience things you otherwise couldn't experience. Maybe it's something that's...
You know my YouTube is like not ever wanting to work for me. But that could be my fault. Alright, the other one, it starts at 4. Oops. Just like 4.
An idea that represents molecules in a way that can be visualized. And it's a more accurate representation of reality than the ball and stick model. But the ball and stick model isn't useless. It helps us visualize and understand many important things about molecules. It also looks pretty cool. Imagine if, instead of making generalizations about how chemicals behave, like water dissolves salts, you had to memorize every single behavior of every single substance. No one would ever get anything else done in their lives. We generalize so that we can free our minds to do bigger and better things. So make no mistake, some models are great even though they're oversimplified to the point of being outright lies. It's important, in fact, to realize that all
Like whose model? The one with the
models are imperfect to some extent. I mean, think of the human models that people compare themselves to. Do you think that women in underwear catalogs and the guys in those black and white cologne ads look like that on Saturday morning after a long night of doing whatever models do on Friday nights? In fact...
Well, that's the part I thought I was going to skip, but you know. Here we go. Thanks. Okay. The one that starts at 4. There we go. There's Lewis. That's okay. I'll show you on here. And I'm videoing for my peoples. Okay. So we're going to talk about, I'll probably start playing in a second.
In understanding how a model represents reality, you also have to recognize the ways that it doesn't represent reality, so that you don't base a bunch of incorrect assumptions on it. Unfortunately, sometimes models aren't merely oversimplified, sometimes they are just downright wrong. And the chemical bonding model is no exception. Over centuries, it's been updated as experimental results have provided information about how the universe actually works. Early scientists, including Isaac Newton, thought that atoms combined because they were literally sticky, or because they had tiny little hooks on them, like a kind of Velcro that held them together. That was their bonding model. In the 19th century...
Sorry guys, I'm going to halt this because this is like jibber jabber right now. So we're going to talk about the bonding pattern that we're going to talk about. It's called Vesper. Write this down. Valence, shell, electron, pair. I know, it's long. Yeah, I will write it down. It's up here on the board too, so. I was trying to turn that down. I think I lost it floating. Valence, shell, electrons, pair, repulsion theory. We call it Vesper. V-S-E-P-R. That's what Vesper stands for. Makes it work. We're going to talk about how atoms can form, and we sometimes like to visualize them. We like to use the geometric shapes as often as we can. So if I find that balloon I just dropped, it's hiding from me. I see it. If I have an atom that has 4 bonds, it's going to have, there's little bitty bonds here in the middle. It's going to have 4 bonds. What do we usually say for 4? Tetra. Guess what the shape is called? Tetrahedron. Okay, so what?
That
Sounds like a triceratops. Yeah, totally. So if we have 4, it's a tetrahedron. If we have 3, I can't work this. There's 3, and they're in a plane. Friggin' old planar. pretty darn close. Okay, it's called trigonal planar. I know, you just gotta make it a little bit work a little bit better. What if I had two and they're in this bent shape? You can try, it's called bent. I tried to tell you. Okay, so we're going to see how these atoms arrange themselves. Now, when I say valence shell electron pair repulsion, what am I actually telling you the electrons are doing? They're repelling. So, water, which looks like, let me get myself a slide here. Water, what's the formula for water? H2O. So what would I draw in the middle, you think? An oxygen. You try to make it symmetrical as possible. Okay, we're going to put an H here on the left and the right. And there's actually these things called electron pairs. Makes it look like Mickey Mouse. So they're called electron pairs. So this is water. It's got an H down here, an H down here, and then there's two humongous invisible electron pairs up here. What do you think the electron pairs are doing based on the words I just told you? Repelling. So these valence electrons are repelling these. Well, what are these? What kind of bonds? No, yeah, they are single. Covalent. Yeah, that's what I was looking for. So those are covalent bonds. Covalent bonds, usually they share two electrons. So this is an electron and this is an electron. This is an electron and this is an electron. And I mean, we don't ever write the E next to it, but I just want to let you know there are two electrons there and there are two electrons here. These lone pairs, why do you think I call them lone pairs? They're all alone and they're a pair of electrons. So we try to, say words that make sense. Most of it's pretty logical. So these lone pairs repel these. These lone pairs are repelling each other. These lone pairs are repelling over here. So what they're trying to do is they're trying to spread as far out as possible so they're not touching, because electrons don't want to be next to electrons. They repel each other. So that's what the whole VSEPR theory talks about. It talks about the valence shell electrons repelling each other, and when they repel each other, they form these cool shapes. So bent, what was the one called like this? Trigonal planar. What if I had an electron pair up here? If you connect the dots, what do you think that is? It's not tetra though. Egypt. Trigonal pyramidal. Okay, so we're going to get into some of the more fancy shapes. But now you got bent, trigonal planar, and 1 to 4? Tetra. The trigonal pyramidal is the one without the atom, so we're going to talk about that too. But I want to talk about that when half my class gets back. So you have paper on your desk. Let me show you how to fold your fortune teller. Yeah.
So do they pretty much like hold each other in place?
The bond?
Or do they like spin?
No, they spin in this little realm.
No, I'm talking about like the whole thing because they're all repelling each other.
Oh, they hold each other in place, yeah. Alright, I'm going to show you the cheap way of doing it. Ready? No scissors required. Ready? You fold a little sailboat. What is paper made of? Trees. What kind of tree? So long. Where's the seed? Lotus, thank you. Alright. So we got our sailboat. Fold your little bottom rectangle piece. We want to take it off. We want to be able to take it off. Use your fingers and really make yourself, it looks like this. All I did was fold it up, so I'm going to take that part off in a second. Make a nice solid crease. This is called the lick and tear method, and if you don't want to lick it, you just have to tear it, but you lick it, it makes it moist, and cellulose absorbs water. See, biology lesson too. Cellulose absorbs water, it weakens. And then you can just go, use my skill for that. If you take the side of your table, sometimes you can go. Perfect. All right, so then you have a nice square. I'll wait for you to catch up with me. I figured you guys know how to make these, but we made these when I was in school too. They've been around for quite some time. So then you take a corner and you touch the middle of your crease. You're going to make a corner on all four sides. So we're making a smaller square at this point. Here's the bottom. See how, thanks, Malin. Cover, and you want to take a piece of paper? Just threw my gum. I used to lead an origami club. Okay, once you get all your four corners, then if you're good to move on, you keep on going. But if you want to watch, this is what I'm trying to do for you. Huh? They stick them together pretty good so that you don't have like folding on top of it. Once you get to this part, you're going to do the exact same thing but on the other side. What you want to do is you want to fold it. Yeah. Right, guys? Yeah, okay, good. Think about the future here. So you're going to fold it so the fold goes on the other side where there was previously a fold. Alright, and as if you get done early, I've sketched on the board kind of what I want you to do. This is an like a review. And then I'll let you guys play the game with each other and then we'll do some other games. Yeah. So ionic, covalent, acid, and orgo is what goes on the outside. If you want to start that, you can. I'm going to unfold it. Just make it work. So here, show everybody how to put this again. And then just make sure it kind of opens its mouth decently. You fold it the opposite way. So that you're gonna have a four square in the middle of the end.
I made one of these last semester.
I don't know. I'll hold it in the middle. The folds are there.
Just in case you need some inspiration for next word. Just you want me to do it.
Sometimes it's nice to fold it, like that first. The square folded half first on the side so it's flexible. But I'll just show you mine real fast. Find it, there we go. So it opens up, got a mouth going this way and this way. I know we're still working on this. So you see, so what I'm going to put the view over ahead, I'm just going to show you this now and then not shaken. I put my numbers on this side. So I just chose, your numbers are randomly 1 through 8 on each of the triangles on the inside. I can show this on the document in just a second. But then, so like for 5 and 6, they're together on the same flat. I chose to make that my ionic version. I did one formula and one name. Make it complicated, like you're going to be challenging each other. You can go copper 2 perchlorate dihydrate. Go for it. Okay? You can totally do that. So for every one, you're doing a formula and a name for that category. You can see it up here on the board if you need to get closer, go closer. It's just like that first to it. Now we're talking about so this looks like a velociraptor. Yeah, I was so on the inside. Oh, okay. You can impress your friends. Okay, so
So loud.
it's okay. No one's judging yours. All right, look up here. Eyes. You see pretty faces? Pretty faces. Pretty faces in the back. Thank you. Okay. So 1 and 2, I just put as my ionic one. I put one name or one formula and one name. Both ionic though. And then 3 and 4, I put 2 covalent ones, one formula and one name. If you need your problem set for inspiration, use your problem set for inspiration. Do not use mine. Cheater, pumpkin eaters. Okay? Acids, they have their own little tab. I just chose 7 and 8 for my acids. And then my orgo, I chose that one. I just chose the last one. So every little duo is its own category. I did SE and that's methane. You're choosing 2 compounds, 2 different compounds. Yeah, okay, I want this done in the next 7 minutes. Oh Lord, she wants this on time or something. We've got lots of time, won't forget. It doesn't correlate. I just said choose the tab. It doesn't have to be done. I'll show you outside. If you want a marker to make it pretty and colorful, just keep it to the rest of your life. I can wait so but yep, so one zero one three. So you do it like this. Yep. You skip over my first part, I actually look at the other first. I don't know what you do. Okay, I'm ready to open this up to 2 and so you just like take the toilet. Okay, so it's really, guys, listen, don't stress. Open up a tab, let's call it a day. Put an ionic formula and an ionic name. With the number it's quite okay. I just want 2 of every single one. But don't put like NaCl and then put sodium chloride. I want you to be creative. Use some of those polyatomics. As long as you have 2 of everything on there, you're good. Steven, jump on this. Megan, you need me? No. You are doing compounds. Like you're what do you mean? I want you to write the full name. Yeah.
So it's
Yes, ma'am. I'm gonna put mine up here as an example. The formula is like you writing NaClO3. Oh, the yesterday where I showed you the like 2n plus 2. So for today, this morning when we did butene, butene would be C4H8. But the word for that would be butene. Okay, so that's what I mean by formula. Yes, ma'am, I will. Let me zoom in real fast and leave this up here. Here's me. Yep. You wait, like, are you done? Okay, go super fast. Like lightning. Lightning. Alright, speed of light, yeah. So you can see I've got I've got my ionics split because I did it like that, but as long as you get 2 of everything on there, you're in good shape. I'm going to show you over here. So like, give me a meth, F, probe, or view. Which one? F is two carbons. Let's do ethane. So ethanes have all single bonds. H is all the way around. Single bond means it's an ethane. So then all you do is count up. You have two C's, so C2, 1, 2, 3, 4, 5, 6 H's, H6. So this is the formula for ethane, but if you wanted to, you could write ethane like ETHAN, and someone would tell me the formula.
Okay, you got it.
Okay. All right, who's got theirs done? Raise your hand. Okay, I'm gonna give you a minute and a half. Yeah, you're done? All right, study your polyatomics now. I'm gonna see how much we know without our list. Oh, this is gonna be a competition. Not playing. Competition. Oh. Look at those polyatomics. Okay. All right, so looking at the first one, I went ahead. You'll see there's parentheses in two places because I have to put them, because if I didn't, that would look like what? That 4 and that 2 would go together, look like 42. That would look crazy, right? Okay. Find something to write on. It's not talking. Thank you. So what's the name of that NH4? Ammonium. Ammonium. That is one of your big polyatomic ions. It's called NH4, 1+, ammonium. And then what's the S going to be here? Sulfide. How did that 2 get there? From the sulfur's charge. S2- crisscross down. And so that's why I have to put parentheses around ammonium, because I can't put 42. It has to be 4, 2. Okay. This obviously is what? It's an acid, because we see that H in the front. Binary acid or ternary acid? Ternary acid, so it's a big acid. Do I say hydro or not? No, I don't say it. So this NO2 normally is called what? Nitrite. How does it change? Nitrous. Acid. You still have to say acid, because I need to read that it's an acid as well. Remember the ite in us, the tendinitis is how you remember that. And ate to ick is how you remember that one. Yeah.
Usually say hydro or
When it's just H with one other, like this one.
Okay.
So what's the name of this one? Bromic, right. So it's like bromide, but you drop the I to go ick. And you still say acid. Is your question?
Attention FFA members, please meet outside the Hort Lab next to the water tank for a quick picture before you get on the bus.
First name? All right, so we know it's potassium.
For track, there will be a mandatory track meeting at 2:20
C204.
in the cafeteria. And for Black History Month, the question of the day was, when did Lincoln's Emancipation Proclamation become effective? The answer was 1863, and the winner is Elizabeth Moore. Make sure you stop by the Black History Month table during lunch to be entered in a drawing to win a free ticket
Don't
to
say try lunch.
semifinal. Thank you.
I need to know the charge of chromium. That's what I'm asking.
Chromium 3.
Chromium 3. How do I know I have to do that? Because chromium is a transition metal, and it has one of those ones with variability in its charge. So it's chromium 3 oxide. Next one. Automatically, you guys see what's the first thing?
Oxygen tetra.
Right. So you see it's a non-metal. You go, oh, I don't need no charges. Let's just say what I see. Oxygen, and then I see 4 chlorine, so I have to say tetrachloride. So oxygen, tetrachloride. I'm going to go the other way now, so I'm just going to stop these for now and go from the name to the formula. These you have to probably write down your charges and crisscross on your paper someplace, okay? So you see BA, oh man. Okay, peace out, bye. I have a Chem Club meeting today. If you need to be here, I will be in Chem Club mode. I'm going to try to go back and forth. I'm going to take it on so I want you to ask me questions if you need to. Yeah, okay. Yeah. Comes at what? Wait, oh yeah, I'm sorry. The green guy. It's on the website.
Oh, so we have to read.
No, it's on the website, so I would expect you to really look there because I just updated the website and sent out a big huge text yesterday. So.
I
don't get the text.
You're on.
So it didn't work for us. I just download the app.
If you can download the app, it works a lot better. Yeah. I didn't take it up because I want you to ask me questions, the ones that you maybe didn't ask in class, and it's a good study resource if you did the answers right anyway. So I didn't want to take it from you because I think you should use it for studying. Hey Molly, look at my atoms.
So guess. Sorry.
Get the fuzz off the
So
butt.
guess who